We are going to have a quiz again next Tuesday. As I told you, we're going to have to do quite some quizzes to catch up with everything. This is going to be on the interval of convergence. So this is material, if you want, from 6.1, defining the radius of convergence of a power series, or perhaps the interval of convergence, which is a bit more. Okay, I'll do an example of each. So let's start with the radius of convergence. So let me just start with an example. So suppose we have the following series here. I take deliberately a little bit more complicated things so that you kind of see everything that can go on. In fact, there's a square here. It's kind of a bit complicated, but it's good to see. And on the test, probably I'll do a little bit simpler. First of all, what's the center here? It's always good to notice this. The center is 6 here, right? Okay. And so the ratio test that we have to do, it's always the ratio test. We take the limit for n going to infinity. It's a big fraction in absolute values. Don't forget the absolute values. N square x minus 6 to the power n, 8 to the power n divided by 2n factorial. That's just copying. Now, this is essential, is to write this correctly. Replace every n by n plus 1, and perhaps better, replace n by n plus 1 between parentheses, in case there's ever any doubt what to do. Okay, and then we have x minus 6 to the power n, that becomes now n plus 1. Then we have 8 to the power n, that becomes now n plus 1, divided by in 2. Now remember, replace n by n plus 1 in parentheses. And the word parentheses around this whole guy, so that's why I keep writing more parentheses there, okay? Good. Absolute values only apply really, because there's nothing else is negative here, to the x minus 6, okay? So we can already, if we want, get a little bit, get rid of them. Okay, so what do we have? On top we have this n plus 1 factorial squared. This might be not immediately clear, but it's actually, with factorials, it's better to just write it as 1 times another. Often we don't do that with squares, but this one, it's better. So then we have x minus 6 to the power n. I'm going to run out plus 1. I'm going to run out of space. Okay, I'm going to start over here. So this is the limit for n going to infinity. Okay, here we go again. So n plus 1 factorial. So this is what the one I'm looking at now, but I'm going to break it down like this. Then I have the absolute value x minus 6. Very important absolute values there, okay? And then 8 to the power n plus 1. And then also this guy will come on top. So 2n factorial. Good. And so what we have now in the bottom is this n factorial squared is n factorial. Then we have an x minus 6 to the power n. We have an 8 to the power n. And we have the what we have now. This is the guy that we get in the denominator here. That is 2n plus 2 factorial. Okay. Last time we discussed a little bit more about this 2n plus 2 factorial. So remember what we need to do here. Well, there are a couple obvious simplifications, namely this power of 8 cancels everything out, so we have a power 1 left, and the same here for this guy. So 1 left. But the others are factorial, so we have to rewrite the factorials, and I'll do this here. So n plus 1 factorial, that's the bigger one in terms of the smaller one. Okay, that's how we do this. It's n factorial times n plus 1, one more. And then here, this is the bigger one, so 2n plus 2 factorial in terms of the smaller one, that is 2n factorial. We have to go from 2n to 2n plus 2 in steps of 1. That is, the first one is 2n plus 1. We are not there, so we have another one, 2n plus 2. Okay, so we can now replace everything. So this is the limit for n going to infinity. N plus 1 factorial. So I'm now doing this formula. That is n factorial times n plus 1. There's another one, so I do this again. We had the x minus 6, and we had the 8. And then we have the 2n factorial that we don't touch because that was a smaller one. In the bottom we have the n factorial, those other two guys are gone. And then finally we now use this formula. We have 2n factorial times 2n plus 1 times 2n plus 2. okay? And so what happens then, again, these factorials now all go away. That's what's so nice about these factorials. And we are left with this guy. There's one more simplification you can do. It's easier if you see it. Otherwise, it takes a little bit longer to calculate the limit. Namely, this is really 2 times n plus 1, right? So if I cancel the n plus 1s with one of those, there's a 2 left. So what am I left with if I do all this? The limit... Oh, well, first of all, these two guys don't depend on n, so I always prefer to have them outside. Okay, that makes it much better to see what I have to do with what remains. Limit. But remember, if there's an n involved, you cannot bring it outside. So this n plus 1 has to stay, and that's really the only one on top. And in the bottom, we have a 2n plus 1. Okay. Now this limit, again, very quickly, we divide everything by the highest degree term, which is n here, and so we get that this is 8x minus 6, limit for n going to infinity, 1 plus 1 over n, 2 plus 1 over n. These reciprocals here are going to 0, oh, hello, go to 0. And so finally I'm left with 8 times x minus 6 times 1, which I don't write. Now, remember, this is always a condition, right? The ratio test, we're doing the ratio test, we have to say that this has to be less than 1. So, in this case, we have this less than 1. So 1 is the rate of convergence? No. You have... Oh, what am I saying? People, I'm going too fast here. First of all, I forgot a couple of things, right? Jesus. Here, there was a 2 here. I forgot about that 2. So that 2 should also come out here. And then this is a half, not, I don't know, the limit here is a half, not 1. So sorry about that. Okay, let's get rid of this guy. So we have, so rewind a little bit here. So let me say, so when I canceled this n plus 1 with this, I was a 2 left. So that 2 has to go here. And then if I calculate this limit, I have a half, right? Because, I just said it, 0, but it's 1 over 2. Okay, and so we have this 2 there. Okay, now we are somewhere, well, what we get. Let me write it, simplify this first. Divide by 2, so we have 2 times x minus 6. So now we say that this has to be less than 1, and we solve for x minus 6. In this particular case, this means we have to divide by 2. So we get x minus 6 is less than a half. And therefore, this is the radius of convergence. Okay? What does this mean? The center was, what was the center? The center was 6. So here is 6. And we go 1/2 to this way, that's 6.5. I don't know, 6.5, let's write it this way. And if we go a half this way, we could in 5.5. And so what we so far have said is that in between here, we have convergence. And outside, we have divergence. But then there is the issue, what happens in the endpoints, right? So when I say, when do you have to check these endpoints if I ask for the radius of convergence, then, so the radius of convergence, you're done. But if I ask for the interval of convergence, you have to do more work. Now, I'm not going to do it for this one because it's an awful series that you get then on the endpoints, which you have no methods to solve. So, but I'll do the next example that I give, involving slightly different things, but again, you'll see now, so in this one example, let me write it, so what's the interval of convergence? I'm going to ask. So make sure that you read the questions always properly to see, is it interval or is it radius? If it's interval, you have to do more. You have to do the radius anyway, but the interval is more. What does that mean? Well, the interval means that you're going to have to look at the endpoints now, right? But okay, as I said, we do a new problem. This is the problem I'm thinking of. Infinity, 2 to the n, x plus 3 to the power n, oh, minus 1 to the power n, sorry, I forgot about that guy, n cube, 6 to the power n. Okay. So, ratio test. That's always what we do. We take the limit for n going to infinity, big times. Okay, we have minus 1 to the n, then 2 to the n, x plus 3 to the n, over n cube, 6 to the power n. same on top, except all the n's become n plus 1s. Be careful, it's n plus 1 cubed, not n cubed plus 1, because it's n that are replaced by n plus 1, and that whole thing get cubed. Okay, and then 6 to the power n plus 1. Okay, that's equal to, let's write this. First of all, what about the absolute values? Well, I don't care about this, because it's either positive or negative, minus or plus 1, so since I take absolute values, they don't matter. And then the only thing that I have the absolute values for is these guys, right? And then I can get rid of my other guys. Okay. So now I have to write this also. What do we have on top? Let's look at the top part first. 2 to the power n plus 1. You have this x plus 3 in absolute values to the power n plus 1. So by the way, what's the center here? I should have perhaps started with that. Someone might say 3, but it is negative 3, right? Because the center is always x minus c. So what you need is negative 3 to get minus minus to get a plus 3. If you, another way of saying that, what you can do is always you can say, okay, let's put this equal to 0. The center is exactly where these powers get equal to 0. And if you solve, you find x is negative 3. Okay, so that's where this negative 3 comes from. Okay, what else? Then these two guys are going to come in top. And then we have the corresponding guys in the bottom here. The 2 to the n and the x plus 3 to the n. Of course, there always has to be matching, right? Because that's the whole thing. We replaced everywhere an n by n plus 1. Some go on top, some go on the bottom. So be careful. Don't just start writing everything out with n plus 1s in the top or something like that. Okay, so let's do the simplifications that we can do right away. That are the powers always, the exponentials here, right? If we this one with this one have a 2 left, this one with this one have a 6 left, and then this one with this one have a power 1 left. And now, so let's see what we have. What's left then? If you get rid of the n's, then I'm going to take it out. So okay, so I should perhaps let me write my equal sign a little bit more here. So I can take already the 2 out, this 2. I can take this x plus 3 out. And I can absolute values, right? And I also can take this 6 out. So then I don't have to worry about it anymore. So now I can see much clearly what is my remaining limit. And especially, like, see this expanding here is always really not what you want to do, because these limits are much easier if you don't expand them. So we have x plus 3 over 3, I'm just simplifying, and then I just think of this, okay, I take this whole thing inside one single cube, and in fact I can even take the limit inside this whole cube. The limits are very nice. You can move them around almost everywhere where you want, because all these functions are continuous. Okay, so now this limit inside, we know exactly what to do. We can divide here by n, and by n. So this would give me, so what do we have then? Okay, let me go a little bit here. So again, x plus 3. Wait, I said I want to simplify, and then I said 6 here. What is that for silliness? Okay. X plus 3 over 3, so x plus 3 over 3. By the way, it's a bit late, that's why I'm making this. You can see my date stamp there, right? Okay. All right, and then so now this limit is the limit. We have a 1 over there, and 1 plus 1 over n to the power 3. And so this n goes to 0. And so this is actually just 1. Okay, so I'm not going to write this anymore. This is just x plus 3 over 3. Now, remember, what we do is, in the ratio test, we put whatever the limit that we get less than 1. So we put this less than 1, and solve for x minus c, in this case, x plus 3. So we have x plus 3 is less than 3, and so this is the radius of convergence. What does this mean? This means that if I make a line here, the center is negative 3, so I will be centered at negative 3 here, and I go 3 to the right. I hope you see that ends you in 0, and if you go 3 to the left, you end up in -6. So inside, okay, again, try again. Outside, we have divergence. Inside, we have convergence. That's the meaning of these things. But the question was not just the radius of convergence, it was the interval of convergence. Okay, what does that now mean? That means we have to now concentrate on these two endpoints here. These are, oops, I'm wrong. These two endpoints. And how do you find them? Well, either you do it this way, or it's the same thing as solving this equality now. X plus 3 equals to 3. Okay? In case you rather do things algebraically, but you see it on the picture much easier, I think. I think it's easier that way, but okay. Whatever floats your boat. Okay. Good. So, what does it now exactly mean? So the interval of convergence. So this was the radius, and let me write it here in case you later come. So the interval of convergence, so that's not the question. So we have the two endpoints, x is -6, and the other one, I'll do it here, x is 0. Well, what you do with this x minus 6 and x is 0, you plug them in the original series. So they will be plugged in here. So now I'm going to put in -6, so this will become -6. So -6 plus 3, that will become -3. So I have summation -1 to the power n. I cannot, now this -1 to the power n plays a role, right? I'm not taking absolute values anymore. I have 2 to the n. And then I have -3 to the power n. That was plugging in -6 in here, right? And then on the bottom, I have an n cube and a 6 to the power n. Okay, now, if you do this correctly, a lot of things are going to cancel. In particular here, if you, well, first of all, when you have a negative sign inside the power, take it out, because otherwise you're going to get confused yourself. So I'm going to do this. I'm going to -1 to the power n, and then that's the one that I originally have, 2 to the n, and another -1 to the power n, 3 to the n. You have to pick, when I say take it out, I mean, what we're using is that if you have a product to the power n, that's a to the n, b to the n, right? I'm going to use this again, so I'm saying this already. And okay, and then in the bottom I have 6 to the n. So going back with this formula, what is this 2 to the n and 3 to the n combine as, if you have the same exponent, then you multiply the bases. Okay, so I get summation. Okay, well now what happens with this -1 to the power n times -1 to the power n? Well, that is -1 to the power 2n, but it's kind of a bit misleading if you write it like that. You might now start thinking weird things about it. 2n is always even. So this -1 to an even power is always 1, right? So, well, in other words, it's much better to convince you already right away, oh, but the product of these two numbers here, these two guys are either both -1 or both 1. So if I multiply them with each other, they're always 1. So they cancel. Okay, so they cancel. Oh, I forgot my n cube here. So what is left then? The top is 6 to the power n, the bottom is n cube, and the bottom is 6 to the n. Okay, so everything cancels, so I get the summation 1 over n cube. Now, is that not nice? Because that actually is a p series, and p is 3 here, and p bigger than 1 means convergence. For some reason, in one of the quizzes, in quiz 4, I think a lot of you thought that p less than 1 was what you needed to be. So I've warned you for this. Every test, it's always about not 0, equal to 0, not infinity, equal to 1, less than 1, bigger than 1, and it's always a different. So really, really make sure that you have the various tests separately. Okay, don't confuse them. Okay, so convergent. So okay, this means that this guy is part of the gang, of the green gang. So it's included. If it would be excluded, I would write an open circle like that. Now, we don't know yet, so let's see what it is. I plug in x equals 0. Okay, summation -1 to the n, 2 to the n. And the only thing that changes now, this becomes 0. So that's actually just 3 to the power n. And then in the bottom I have n cube, 6 to the n. The 2n, 3n again combine as 6 to the n. And then in the bottom also 6 to the n, we have also the n cube. So these 6 to the n's cancel, and we get summation -1 to the power n, 1 over n cube. Now you can say, this is, I can do the, it's an alternating series, so I can do the alternating harmonic series test. Alternating series test, sorry. Sure. So, okay, let's do it. Alternating series test. The limit for n going to infinity. Remember, you now ignore the sign and you have to calculate the limit, which is ridiculously simple because it's 0. So yes, convergence. You could also have actually said, well, this is if I take the absolute values, I get a p series, and there's a convergent one. That's what we just argued. In other words, this series is absolutely convergent. Now, in general, when we do with endpoints, we don't care about that, but it happens here. I'm just pointing that out. So we get convergence, meaning, again, this guy is also part of the party. And for some reason, this guy had gone. Okay. So this is one way of writing it. Another way is writing that the solution is, so the interval of convergence, where is it here? The interval of convergence is equal to, I'll write the answer here, is equal to including -6 and including 0. That's what these square brackets do. Okay. All right, so you have an example of each, and in the quiz I will ask either. I could ask either or other one. Please read the question always carefully.